All right, in this next example, example 3, we are going to look at the formulas, the summations, for the right, left, and midpoint approximations to the area under the curve. Now we are incorporating summation notation. So, example 3. Determine both the endpoint, so left and right endpoint, and midpoint approximations to the area under the curve of x squared on the interval 0 to 4 using 8 rectangles. So, for all these problems, it's pretty useful to draw some sort of representative picture. It doesn't need to be perfectly accurate, but it should be representative. So, what I'll do is I will just draw, zoom in a little bit here. We'll draw a quadratic. There we go. So there is our x squared graph. So our function f of x equals x squared. And we're going to have 0 to 4. So then there's 2. And then we're going to have 1 and 3. And we're going to split it into 8 rectangles. Right now, we've subdivided this interval into 4 evenly divided pieces. But we need 8, so we have to further subdivide this. So we'll have a half, 1.5, 2.5, 3.5. Okay. So we're trying to figure out the area under this portion of the curve. We want to estimate this area here. So let's go ahead and draw. Let's go ahead and do the... we're going to use this graph a couple of times. So for now, we'll start off by doing the... Let's start with the left endpoint. So we'll do L sub 8. It's the left endpoint approximation using 8 rectangles. So to do this, when we draw our rectangles, we are going to be determining the height of the rectangle using the left endpoint. So for instance, on this first little rectangle right here, this is the base of that first rectangle, the left endpoint is right here, and which is 0. So what is f of 0? Well, 0. So the first rectangle has a height of 0. The next rectangle has a height of f of a half, so has a height of a quarter. So there you go, slightly bigger rectangle. And then here, this is going to have a height of f of 1. The next rectangle will have a height of f of 1.5. Next rectangle will have a height of f of 2. Next rectangle will have a height of f of 2.5. And I think you get the picture. There's a picture for our L8. So, generally speaking, what we do when we set this up is we have our interval. So our interval, 0 to 4, this implies that our A value, our starting value, is 0. Our ending value, B, is 4. Since n is 8, this implies that the change in x, so the width of each rectangle, is going to be b minus a over n, which is a half. So now, for the left endpoint approximation, you can see up here that we're supposed to be using f of x sub I, and down here they tell us that x sub I is this. So this means that x sub I minus 1 is a plus I minus 1 delta x. So x sub I minus 1 is a plus I minus 1 delta x. Or we just have this written as I minus 1 over 2. So then we can go ahead and say, okay, this means that f of x sub I minus 1 is this whole expression squared, which we can write as I minus 1 squared over 4. So L sub 8 is the sum from I equals 1 to 8 of our f of x sub, f of x sub I minus 1 delta x, which is our sum 1 to 8, our function I minus 1 quantity squared over 4 times our delta x, which is 1/2. So now, much like with a limit and with a derivative, we can factor out any constant multiples. So here we've got a 1/4 times a 1/2. So we could pull this out to have 1/8 the sum from I equals 1 to 8 of I minus 1 quantity squared. So now our power sum formulas, we know what an I squared is, but we don't have anything for I minus 1 squared. So what we're going to have to do is we're going to have to expand this outward first before we use the power sum formula. So this would be the sum, 1/8, the sum of I squared minus 2I plus 1. Okay. So after that, we can continue. But what we'll end up doing here is we can distribute the sum through. So I'd write this as 1/8 times the quantity, the sum from I equals 1 to 8 of I squared. Again, I can factor out constants out from the sum. So I can write this as minus 2 times the sum from I equals 1 to 8 of I plus the sum from I equals 1 to 8 of just 1. And now all three of these sums are formulas that we've talked about. So this would be 1/8 times this sum, our capital N value is 8, so this would be, for the quadratic, this would be 8 times 9 times 2 times 8, so 16 plus 1 is 17, all over 6, minus 2 times, power sum for this would be 8 times 9 over 2, plus this would be 8 times 1. If you do all the arithmetic and add all that up, you will get, where are we here? 35 halves. There we are. Okay, so that's the left endpoint approximation. For the next approximation here, let's just cap this off. We don't specifically need to draw the picture to do this, but just so you can see it, the right endpoint approximation again, we have the same thing. We have A equals 0, B equals 4, delta x equals a half. Our n is 8. We also have our x sub I, because if you look above here, for the right endpoint approximation, we don't need x minus 1. We just need x sub I. So the difference here is when we are at the first rectangle, we're using this first point here for the right endpoint approximation, but for the left endpoint approximation, we're going to use this point. So when you label these little tick marks here, we start with 0, x1, x2, x3, x4, all the way up through x sub n. So for this rectangle here, the first rectangle, or let's even just think about the ith rectangle, this right endpoint would be x sub I, the left endpoint would be x sub I minus 1. So x sub I in this case is going to be just, well, 0 plus I delta x. Since delta x is a half, this is just 1/2 times I, or I over 2. Which means that our function, f of x sub I, is just I squared over 4. So if we draw these rectangles, our pictures look something like this. Now you can compare the left and the right endpoints, and for this particular function, the right endpoint approximation provides an overestimate because we're taking into account these little areas here that overhang the function. So we're going to get an overestimate. Whereas for the left endpoint approximation on this function, we had all these little gaps we left unaccounted. So we ended up getting an underestimate using the left. Now the left doesn't always provide an under, nor does the right always provide an overestimate. It would depend on the curvature of your function, whether or not it's increasing or decreasing or monotone. Okay. So to continue here, r sub 8 is the sum from I equals 1 to 8 of f of x sub I delta x, which we can replace in some information. This is I squared over 4 times a half. Again, we can factor out the 1/8 constant that we have. And then we just have this power sum formula for the quadratic. So this would be 8 times 9 times 17 all over 6. Which is 51 seconds. Okay. Now for the midpoint, what we want to do here is, for each of our rectangles, we're simply going to use the midpoint. So again, A is 0, B is 4, delta x is still a half, but what does significantly change here is that, n is still 8, but our midpoint, I'm going to call this x bar for the midpoint. This is in statistics, bar usually means an average. So I'm going to call this x sub I bar because essentially for the midpoint, we are taking the average of the two left and right endpoints of each little subinterval. So our midpoints would be here, 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 here. So we still have our regular old rectangle width, but our height is going to be determined by that location. So again, there's the midpoint to the best of my ability. So you draw your rectangles here. We're still going to just draw a line, oops, too tall. Draw a line, So there we are. There we are. So we found the height by sampling at the midpoint of each subinterval. Now, if our function that we're trying to approximate the area under the curve, in this case x squared, is a monotone function, which it is, x squared is monotone, it is increasing on this interval 0 to 4, then this means that the midpoint will provide a better, more accurate result than the left endpoint or the right endpoint approximations. This is going to be somewhere in between. The left endpoint was an under approximation. The right endpoint is an over approximation. The midpoint will still be either an over or under approximation, but it will be more accurate. It will be closer to the true value than L8, and it will be closer to the true value, closer than R8. So, what we can do here is come up with an expression. We want to simplify this a little bit more. So let's bring that down here. So x bar sub I is, I'll write this as a half times x sub I minus 1 plus x sub I. So this one, we found out what this was from earlier, right here. This is just I minus 1 over 2. So I minus 1 over 2 plus x sub I, we found out x sub I was just right here, so I over 2. Well, it looks like we can add this all together. This is really a half times I minus 1 plus I over 2, which is 2I minus 1 all over 4. And then, if we do f of x bar sub I, this is 2I minus 1 quantity squared all over 16. This one we can factor out, or FOIL out, I should say. This would end up being 4I squared minus 4I plus 1 all over 16. So then M8 is the sum from I equals 1 to 8 of this expression, so 4I squared minus 4I plus 1 over 16 times delta x, but we know delta x is 1/2. So a half. So we can pull out the 1/32, and then we can distribute the sum and factor out any constants. And the last term would be the sum of 1, but if this sums from 1 to 8, and we're just summing up 1 plus 1 plus 1 plus 1 8 times, this will just be plus 8. Okay. So then, let's see here. We can distribute into 32, and we'll have 1/8, and then our power sum for I squared, which would be 8 times 9 times 17 over 6 minus 4 divided by 32, so minus an eighth. This power sum, which would be 8 times 9 over 2 plus 8 divided by 32, which is a quarter. If you add all of that up, we should get 85 fourths. And now let's look at this. So that is the midpoint. But let's write these all over the same fraction. So L8, as a fraction, we had L8 was equal to 35 halves. But 35 halves is the same thing as 70 fourths. And R8 we found to be 51 halves. So if we get the same common denominator, this would be 102 fourths. The reason why we would get a common denominator here is when you compare the size of fractions, it's helpful to have them all with the same denominator. So you can see that 70 is less than 85, and 85 is less than 102. And in general, what we will have in general, if our function, so if a function, if f is monotone, we will have, well, in this case, let's just say increasing. For increasing, we do have the midpoint is going to be sandwiched between the left and right endpoints. If our function's decreasing, then this inequality the directions of the inequality flip.